So let's introduce that. So let's say R is an edge-weighted graph. If that means we have some weights on its edge. And usually this weight is between 0 and 1 for its edge E in this graph R. Sometimes, we can further consider this R as a complete graph by giving weight 0 to all non-edges of R. The non-edge UB of R. And for a given graph F, and a map pi, which is a vertex map that maps the vertex of F to vertex of R, we consider for this pi, we can compute its number. So what's this? So let's say F is triangle. If R is edge-weight graph with 1, 0, 0.5, 0.5, 0.5, and assuming that your pi maps these three vertices in this way, and we multiply these three, which is like for each axis in F, you consider the weight on this edge and you multiply. What is this? So this is exactly when you have like x1, x2, x3, then v1, v2, v3, and then this is epsilon regular with the density, say d1, 2, d2, 3, d1, 3. Then number of triangles that we get from the triangle remover, triangle counting lemma is what? You multiply these three and then you multiply this three number, plus minus some epsilon times some error term. But the multiplication of these three is actually this. So what you get from this triangle embedding was multiplication of this. And then that's exactly what you get here. Once this pi indicates which vertex has to go to which height of the epsilon regular partition. So that's the motivation for this definition. And furthermore, we define without this subscript, just home of F and R is the ones you consider all possible maps, and you consider this, and we call this the homomorphism number when F to R. If R is just a simple graph, so meaning that the H rate of R or 0 or 1. Then what? Then this number is 1 if this pi is a homomorphism, graph homomorphism, 0 otherwise. So this simply counts, so this can be identified with the simple graph, and this case, this home FR just counts the number of homomorphism. Okay, and let's also write the auto of A with the number of automorphism of the graph, which is the graph isomorphism from F to F itself. So using this concept, we can take the counting lemma. So suppose that for given gamma, all other number n are epsilons are sufficiently large. N is sufficiently large, R is sufficiently large. Technically, yeah, let me just write it this way. Depending on the situation, sometimes R does not have to be much bigger than gamma, but yeah, let's write it in this way. And let G be a graph with an equitable epsilon regular partition. P1 to PR. And let R be an epsilon 0 unit graph with H weights Wij being the density between Pi and Pj. Then the number of copies of F in G can be approximated by the homomorphism number of F to R divided by the number of automorphism, and you take the N over R, and then you take the power of the order of F, and that is error term, the gamma times N to the number of vertices in F. So you name the amount of error that you want to allow, and if other parameters here are sufficiently small, then you can bound it in this way. And also the removal lemma can be generalized to more general graph. For a graph F and epsilon positive, there is delta such that every graph with fewer than delta times n to the number of vertices of F, copies of F, and this can be made F3 after removing epsilon x squared z. And both counting lemma and removal lemma can be further generalized to hypergraphs. But okay, for removal lemma, the statement is also analogous for hypergraph. But the counting lemma, it's more complicated. So we actually need to define a different concept of regularity called, strong regularity. And yeah, it's a bit more complicated, so we will not talk about this in here. But it's good to know that their hypergraph version also exists. Okay, so finally we give a proof of the regularity lemma. So there are many different proofs of this regularity lemma, but perhaps most standard one is using something called energy increment argument. So basically you take some partition. So we consider the weaker version that we don't need to consider, we don't have to get the equitable one. So, and what we do is if this partition is not good, meaning that between here, it's not epsilon regular, then you can find some parts whose density between them is either too large or too small. If we find such a partition, such a part, then what you simply do is you make a further partition. So you divide this here, and you keep repeat. And while you're doing that, you have to show that this can be, this can be finished in finite amount of time. And in order to show that, you define something called some energy. Then you show that every time you do this, if energy increase, and this energy cannot go beyond certain point. And using that argument, you can show that it actually finishes within finite amount of time, giving you the bound on the number of parts. And yeah, that gives us the regularity lemma. And that proof was actually done in the advanced graph theory lecture notes and lecture video that I put on my webpage. And this time we want to consider other proof. There is this proof using spectral method. And this proof was by Tao and independently Segedi. So now our aim is to find the 100 epsilon regular partition. Okay, so let the vertex be the number between 1 and n. And we consider the adjacency matrix of G. So we define this adjacency matrix in the introduction to the graph theory course, and then we learned some basic property of this in that course. So one of the basic property, so the adjacency matrix is 0 or 1, so you have a 1, 2, 3 to n, 1, 2, 3 to n. And I comma j is 1 if there is an edge between I and j, otherwise it's 0. So in fact, this is a real symmetric matrix. So there exists this eigenvalue decomposition. So UI is the eigenvector where its eigenvalue lambda I satisfies that let's write that in order of its absolute value size. Lambda 1 is the biggest and lambda n is the smallest. And you want to un that forms orthonormal basis. Okay. Let's first consider some upper bound of the size of this lambda I. Since we care about its absolute value, which can be computed by taking square, we consider a square. And what? And then we consider the trace. And that's summation of lambda I square. But what's this? This is same as the number of length to walk in G. But the closed walk. Length to closed. But how can you obtain a length to closed walk? You start from here and then you go and then you come back. That's the only way. So this counts the number of edges, which is the most n square. And this is how we enumerate them. So for arbitrary j, this is at least j times lambda j. So this implies that for each j, the size of lambda j is at most n over square root of j. So we have this. Now let's consider some sequence. Say big T, the capital T of 1, let it be 1, and big T2 is like 2 to the 4 times T1 square divided by epsilon square. And in the same way, Ti plus 1 is same as 2 to the 4 Ti square divided by epsilon square. This determines the sequence. And we consider the interval. Say I1, I2, where I sub I starts from Ti, and then ends at Ti plus 1. Okay, and let's say it's an open interval here so that they are disjoint. And what do we know? As summation of lambda I square is at most n square. So we consider this interval up to, say, 1 over epsilon cube. Then the summation of, say, I equal 1 to 1 over epsilon cube, then summation of the I in J in, that's right, K, L in I sub I, and I square. This is at most n square. So by Pigeonhole principle, there is certain J such that the summation of all indices here is at most epsilon cube n square. Okay, together with this choice of j, we fix such j. Now we split the other symmetry into three. So let's say A1 are the ones that come from or small, big eigenvalue. And A2 are the one in the middle. And the middle is this I sub j. And the last one is the small eigenvalue part. Okay, and we will see that this give us structural information about G. So this give us the information about your epsilon regular partition. Then these two will show that their impact on the parts is limited, so that we will show that the epsilon regular partition coming from here is actually epsilon regular partition. So let's consider A1 for it. For each j smaller than tj, each I smaller than tj, we consider ui, this vector. And in this ui, as if you write a column vector, you have this coordinate, and then you see the value of it. And then we categorize these indices depending on the value here. And how do you want to divide? We divide into several parts so that let's say 1 goes to here, 2 goes to here, 3 again goes to here, and the indices in here, we want to make sure that their coordinates are very close. And here also they collect very close. And most of them are quite small. Except there is one part we all collect the big indices with a big value. So we do it. We partition the indices into, say, u sub I, 1 to u sub I, say, let's write it this way, to u sub I to the L, where this L is between this Hughes number a constant number, and one, say, u prime I. So for this fixed I, we partition this into these sets that's based on the coordinate of ui, the value of coordinate ui. Let's write uik is the kth coordinate. And what? This UIL is defined by the order indices k, so that the uik has size between, value between these two. So you see, this is small number and this is large number. So you have very thin interval, and then L is like varying between here and here. So the numbers in UI to the L, their case coordinate is in this very small interval. So K and K prime are both in here. That means the UI is, the case coordinate and K prime's coordinate has almost same value in UI. And this UI prime is the remaining one. So you see in here, what it means is that if K is in UI prime, then the UI K, its absolute value is actually bigger than this times this, or this times this. So that's what? This is bigger than square root of Pj over epsilon n. So we know this. So this shows that this cannot be too large, because what? We know that the UI, if you add all the coordinate and then you squared it, and that's the size of this vector, that's 1, because this is also normal vector. And what? This is at most for all this u prime I, you add the square of this. So this is the lower bound. Because for all this coordinate, its coordinate is bigger than this. And this is what? Ui prime times tj and epsilon n. So if you divide it by this, then ui prime has size at most epsilon n divided by tj. Okay, so we have upper bound on its size of ui. Now we have this partition for each I, for all this one. Now what? Now that we want to now partition the indices 1 to n into group, so that this group, if say K and L are both in this group, then we want to make sure that they belong to the same group in this partition for all I. So how do we do it? But we want to take special care on this U prime. So we let P0 be, you take all I, and you take the union of this Ui prime. So, and take a common refinement of all partitions Uij for all I smaller than Tj. In other words, we take the intersection with I, say Li, or I is 1 to Tj, and we consider all possible L sequence, which is from negative T, say, this to the T, say, minus 1. So L comes from all this sequence, and then L sub I. So for all possible combination, you take the intersection. Then let's say the final partition is a partition B1, B2, BR of all the things outside of B0. Then what? If R is at most, so this is 2 times T to the I epsilon square, 3 over 2. And how many times you take the T sub j? So this is what you get. But from the definition, how we defined this T, we know that this is much smaller than Tj plus 1. Say smaller than this. But now we have this R. Now what? We consider two sets, Vk and say Vl, with K and L different. Then what happened is that for A and A prime, Vk, and B and B prime in Bl, we know that their coordinate, A comma B coordinate and A prime comma B coordinate, the difference is small. We can actually show that this difference is small. Why? What's this? Based on the eigenvalue decomposition, you can write this as lambda I uia uib minus lambda I ui a prime uib prime. So maybe let me write it this way. But this ui and ui b, you can write it as ui a ui b minus ui b prime plus to ui b prime and ui a minus ui a prime. And here, due to our definition of this partition, they belong to the same thing. They belong to the same thing. That means this value and this value are small. How small it is? And most the length of interval that we take it here. So twice of that, twice epsilon to the 3 over 2. Sorry. Yeah, that is correct. Epsilon to the 3 over 2. Tj square root of n. And this value, because we already took care of u prime in B0, as long as it's not in B0, then what? Its value is at most this one. So square root of Tj and epsilon n, net dimension of lambda I. So, and actually you have to take it twice because you have two terms. Okay, and what do we know? On here, so that's at most like the same part here, and then summation of n over square root of j, square root of say k, I. when I is smaller than tj. But in that case, this is because what we have shown before in here. And it's easy to check that this part is at most, say, twice times square root of tjn. And the previous part is square root of tj n over epsilon, like 4. It's almost epsilon, 8 epsilon. So once we know this, then what do we know? And for, say, A in this pk and B in this pl, we know the number of edges in between A and B. That's what you consider the characteristic vector of A and characteristic vector of B, and you compute this AG, and that's like summation of these three terms. And we can consider the first term. So characteristic vector of A transpose times A1, characteristic vector of B is what? You consider all A in A and all B in B, and I am a TJ. You write this. But because of that, everything is up by 8 epsilon. If you take the average, and what? Average value between there, here, let's say, so that EKL is the average value of the entries in A1, PK, PL. This coordinate, you take the average, then this is same as average times A times B plus minus 8 epsilon AD. So now we know the value, and then now we want to analyze these two values. And then if this entire value is pretty much this plus like 100 epsilon AB, the plus minus 100 epsilon AB, then that shows, that's arbitrary A and B. That shows the epsilon regularity between EK and VL. That's what we want to do. And now we consider A2. For that, let capital lambda be all the coordinates, all the pairs KL, such that the borrowing holds. You consider all A in PK and all B in PL, and you consider its coordinate, and you take square, and you add it. If this is bigger than PK and PL, and you put it in this capital lambda, otherwise you don't put it. Then what do we know? We know that if we take all possible coordinate, then you take the square of the coordinate, then that's same as the trace of A square. A sub 2 square. Again, this is like this is basically the same argument as we did before. The trace is same as the number of lengths to walk, which is bounded by the number of ejectory number of edges in G. And now your coordinate in the matrix is not necessarily 0 and 1. So you count the weighted count of this length to work. If an H has a weighted value 0.5, you go and come back, and that's like 0.25, the multiplication of those two. Up to this weighted count, this is the same thing. So we know that this is at most like a trace of this, and our choice, that's at most epsilon q times n squared. Then, what do you know? Then summation of all KL in this lambda, you add what? Due to this definition, you just add epsilon square pk, pl, and that's at most summation of the coordinate square for KL in this lambda and A in pk, B in pl, and that's at most this one, which is epsilon cube n square. Then what do you get? By forgetting this, you get this inequality. So this lambda is going to be the exceptional pair. So we want to show that for most of the pair, it gives you epsilon regular pair, except epsilon r square, many of them. I mean, more precisely, our version was depending on our definition on epsilon regular partition. And the statement there was exactly this. For all pair which are not epsilon regular, if we add this value, then it's more epsilon n squared. So that's what we wanted to get. And from the definition, as long as your pair is not in this lambda, and again, A is in pk and B is in pl, then what? We can again compute this expression as well. You want to add this, and putting this absolute value sign, make it only larger. And here what? You can use Cauchy-Schwarz. And that's what? Square of root of square sum of the square, and you sum the ones, square of the one, so the number of terms is here, and you get this. And what's this? From here, we know that that's at most no, sorry. So at most this. So we assume KL is not in capital lambda. So this is inequality is this way. So you get epsilon square times the size of B times size of B inside of there. So you get what? Epsilon times pk and VL. So that shows that this second term is smaller. Then finally, we want to show the third term. Finally, consider A3. By its choice, all eigenvalues of this A3, we know it's eigenvalue decomposition, so has size and most n over square root of tj plus 1. Because we have shown that this one holds, and for the third one, you only have the small eigenvalue. The eigenvalues for I bigger than this number, c of j plus 1. Then what do you know? We know that this eigenvalue gives us the information about the operator norm of this matrix. That its operator norm is most diff. So here, operator norm here is, it's saying that in that case, what we know, we have this, and because all the eigenvalues are more than that, and thus we have operator norm bounded, then you get that once you multiply this with the vector here, and this vector, then the final value is actually bounded. So its absolute value is bounded by 2 norm of this and 2 norm of this and operator norm here, which is like n over square root of tj plus 1. But what do you know? This, you know, the value of this is most square root of n and most and square root of m, because it has m coordinate and all of them have size 1. So maximum value is this. So total this is n squared over square root of tj plus 1. But what we know is that this is quite small. How small it is? We know that the number of parts in your partition R is smaller than t of j plus 1 to the 1 over 100. So this is in fact smaller than, say, this term, for example, which is smaller than bk, size of bk times bl, times some small number like epsilon squared. Thus, now let lambda star be all the pairs in lambda, as well as the pair that's related to 0. Remember that we have B0, which is weird. Which we define as the union of U prime. That was kind of an exceptional set. And we consider all the small set. Then what? Then with this exceptional one, you can show this. So for this, this value summation was almost epsilon times bk times bl. For this, if you do again, so for this, if you sum it, then that's almost epsilon times n squared. And for this, if you sum it, we know that B0 is small, so it shows a small value. For this, we know that both of them are small. At least one of them are small, so you can also show that this is small. So total, you can show that this is small. So those are the exceptional pairs. And for rest of them, for KL not in this capital lambda star, this inequality, as well as this inequality, as well as this inequality, all holds. So all of them are, we know the value. Then this is small, and this is at most is. So what do we know? No, we conclude that for any A in VK and B in DL with these, we know the number of edges between A and B is same as the characteristic vector of A transpose times A times characteristic vector of B, which is what? DKL times A B plus minus like 100 times epsilon times VK times BL. And it proves the 100 epsilon regularity of this pair VK and VL. And that's exactly what we wanted to show, that this holds for most of the coordinate, and then the exceptional one, if you measure this, then this is small. So that's the definition of 100 epsilon regular partition, and that's truth. Okay, so we have proved this regularity lemma using this linear algebraic facts. Okay, so that's for today. I will see you in next video. Thank you for listening.